Today, we will be exploring the solubility of a gas in water. To review an earlier unit, solubility is defined as the property of a chemical substance called solute to dissolve in a solvent. Throughout the course, we learned that the equilibrium constant for the equilibrium established between a solid solute and its ions in a saturated solution can be represented by Ksp, the solubility product constant. Ksp represents what level a solute dissolves in a solution. A higher Ksp value signifies a higher solubility. A solute's molar solubility can also be obtained from the inverse of the following reaction from the Ksp value. Even for very soluble substances, there is usually a limit to how much a solute can dissolve in a given quantity of solvent. Certain limitations and exceptions to solubility were outlined throughout the course. The first example is the common ion effect. In the event that there was a saturated solution of PbI2 and a common ion, being iodine, was added in the form of Ki aqueous, Le Chatelier's principle states that when the concentration of one of its reactants is increased, equilibrium is shifted in the direction in which that reactant is consumed. The addition of common ions shift equilibrium towards the undissolved compound, causing precipitations, and the solubility of the compound is reduced. The second example is the limitations of Ksp constant. Ksp operates under the pretenses that it is based on ion activities rather than concentrations. Ksp values are usually limited to slightly soluble, essentially insoluble solutes. The third example is the salt effect. In comparison to the common ion effect, the presence of non-common ions tends to increase solubility. This is because higher concentrations must appear in the solution before equilibrium is established. The last example is the incomplete dissociation of solute into ions. Some ions in solution might join in oppositely charged ion pairs. Additional solute must be present for the product ion concentrations to be equal to Ksp, making the solubility greater than otherwise expected. Throughout the Chemistry 112 lessons, we mostly focused on solubility when it comes to solids and liquid solutes. When it comes to gases, solubility decreases as temperature increases. The physical reason behind this is that when most gases dissolve in solution, the process is exothermic. Heat is released and gas dissolves. This effect is very similar to the reason that vapor pressure increases with temperature. Increased temperature causes an increase in kinetic energy. The higher kinetic energy causes more motion in the gas molecules, which break intermolecular bonds and escape from solution. The most common example which relates to our everyday life is soda. Take a SodaStream machine for example. CO2 is pumped directly into water. All carbonated beverages are bottled under pressure to increase the carbon dioxide dissolved in solution. Carbon dioxide can dissolve in water because CO2 is a polar molecule, as is the solvent water. When the bottle is opened, the pressure above the solution decreases and the carbon dioxide bubbles off. This is the reason that sealed pop cans stay fizzy over time but lose their bubbles when you have them open on the counter. The chemical equation for this phenomenon is CO2 plus H2O moves forward to produce H2CO3. We can also note that when a bottle is sealed and this reaction is taking place, the system is in equilibrium, as the forward and reverse reactions are taking place. The solubility of a gas increases with an increase in temperature. The solubility of a gas in a liquid is directly proportional to the pressure of that gas above the solution. If the pressure is increased, the gas molecules are forced into solution since this will best relieve the pressure that has been applied. The pressure law states that for a constant volume of gas in a sealed container, the temperature of the gas is directly proportional to its pressure. When the temperature of a system goes up, the pressure also goes up, and vice versa. The relationship between pressure and temperature of a gas is stated by the Gay-Lussac's law. One example of gases dissolving in liquids in real-life application are deep-sea divers. Deep-sea divers may experience a condition called the bends if they do not readjust slowly to the lower pressures at the surface when they're coming up from a dive. As a result of breathing compressed air underwater and being subjected to high pressures caused by water depth, the amount of nitrogen dissolved in blood and other tissues increases. If the diver returns to the surface too rapidly, the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in pressure. The nitrogen bubbles can cause great pain and possibly death. Another example is in lake ecology. In lake ecology, there are 3 layers which are divided based on their different temperatures. These layers are referred to as the epilimnion, which are warm surface waters, and the hypolimnion, cold bottom waters, which are separated by the metalimnion, or the thermocline layer, a stratum of rapidly changing temperature. When warming temperatures alter the hypolimnion level to too high temperatures, the oxygen available depletes and dissolves out of the water. Fish species, such as trout, which require cold water and dissolved oxygen levels, cannot survive. Thank you guys for watching, and I hope you learned something new on the solubility of gas in water.